Welcome to the Deep Dive.
Great to be here.
This is the show where we slice through stacks of information articles, research, our own notes, basically, to pull out the absolute most vital nuggets of knowledge and insight for you. It really is your shortcut to being truly well-informed. We try to pack it with surprising facts, maybe just enough humor to keep things interesting.
Keep you hooked.
Exactly. And today, we are embarking on an incredible journey, a real deep dive into the very fabric of our planet, Earth, and its surrounding envelope.
Sounds fascinating.
Yeah, we're talking world geography. We'll be exploring pretty much everything from the air we breathe right down to the ground beneath our feet and all the, immense forces that shape it all.
It's a huge topic.
It is. It's all about understanding our world, its places, and how everything's connected in this, profoundly interdependent way.
And that interconnectedness, that sense of everything influencing everything else, that's really the core of why this deep dive matters, especially right now. Geography, it isn't just about, memorizing maps or sticking pins in places on a globe.
Definitely not.
No. At its heart, it's really about the intricate dance between physical phenomena and, human phenomena in every corner of our planet, and how these interactions weave together to design and organize space, right across the Earth. The idea that geography is everywhere really captures this perfectly. Every single thing has a location, right?
Oh, yeah.
And we're constantly moving through and being shaped by these geographical contexts.
That makes sense.
Yeah, and having a solid foundational understanding of geography is, I'd argue, absolutely essential for grappling with so many of the massive global issues we face today.
Like what sort of issues?
Well, think about challenges like global warming, for starters. Widespread environmental shifts, the increasing frequency of natural hazards, the pervasive problem of pollution, even the rapid spread of epidemics, and the complex tapestry of global conflicts.
Wow.
Every single one of those has deep, undeniable geographical dimensions. They happen somewhere, and where they happen matters.
Right. Location is key.
Exactly. So by the end of this deep dive, our hope is that you'll be equipped with a clearer understanding of Earth's systems, helping you connect the dots in ways maybe you haven't considered before, making the world around you feel, clearer and more understandable.
I couldn't agree more. It really is about seeing those hidden threads that link things that seem separate, isn't it?
Precisely.
And speaking of connections, let's start with the one that literally connects every living thing on this planet. The air we breathe.
The atmosphere.
Exactly. Let's transition now to what we can call Earth's vital blanket, our atmosphere. It's truly what makes Earth unique, certainly in our solar system, because life as we know it is only found here.
As far as we know.
As far as we know. And the atmosphere plays this absolutely critical role in sustaining it. This incredible mixture of gases, it completely surrounds our planet, right? Held in place by Earth's gravity.
Gravitational energy, yeah.
And it's not just sitting there, it's actively working. It helps block harmful ultraviolet rays from the sun. It maintains the stable temperatures needed for life to thrive. You just can't imagine life without it.
No, it's essential, a vast invisible shield, like you said.
Right. And beyond those main gases, it also contains things like water vapor, tiny dust particles.
Yeah.
And it's these components that drive all the dynamic changes we see in our weather.
That's where weather comes from.
Exactly. So, okay, let's unpack this. What exactly is this incredible mixture that sustains all life?
It truly is a marvel, especially when you consider its delicate and dynamic balance. As you said, the atmosphere is a complex mixture. Different gases, water vapor, microscopic dust particles, all mixed together.
Okay.
And it's crucial to remember its composition isn't fixed. It actually varies, depending on the time of day, the season, even where you are on the planet.
So it's not the same everywhere?
Not exactly the same, no. But when we look at the main gases, nitrogen and oxygen are the dominant players. They make up a staggering 99% of the atmosphere.
99%, just those two.
Pretty much. Nitrogen accounts for about 78.1% and oxygen for roughly 20.9%.
Okay.
Now, beyond those two, we find other gases in much smaller, often trace, quantities. But, and this is important, don't let their low percentages fool you. They are incredibly important.
Right.
Argon, for instance, makes up about 0.9%. Carbon dioxide, it's around 0.03%, but it plays such a vital role in Earth's climate and, of course, plant life.
Photosynthesis, right?
Exactly. Then there are even tinier amounts of gases like hydrogen, neon, helium, really small fractions.
Trace amounts.
Trace amounts. But here's where it gets really interesting. Ozone. It's present at a minuscule 0.000006%.
Wow, that's tiny.
It is incredibly tiny, but it is absolutely critical for life. Despite its small quantity, ozone gas is concentrated in a specific layer, the ozone layer, and there it acts as Earth's primary sunscreen. It absorbs harmful ultraviolet rays from the sun.
The dangerous UV rays.
The dangerous ones, yes. Without that protection, the existence of living beings and plants on Earth's surface, well, it simply wouldn't be possible.
Okay, so even tiny amounts matter hugely.
Immensely. Then we have water vapor, which is essentially, water in its gaseous form, just floating in the atmosphere.
Right. Humidity.
Humidity, exactly. Its presence is fundamental to life on Earth as it's the ultimate source of all precipitation. All rain, all snow, it comes from water vapor.
Makes sense.
Its concentration can vary quite a bit, though. It can reach up to 4% in really humid, hot regions, but be almost non-existent in very dry areas like deserts.
Okay.
And it also tends to decrease as you move from the warmer, lower latitudes towards the colder, higher latitudes. And it also becomes less abundant the higher up you go in altitude.
Right. Thinner air, less moisture.
Precisely. This water vapor gets into the atmosphere primarily through evaporation from oceans, lakes, rivers, and also through transpiration, which is water released by plants.
Okay.
And finally, those tiny, often unseen dust particles. These are primarily found in the lower layers of the atmosphere. They come in various forms: sand, smoke particles, sea salt blown up from the ocean.
Stuff floating around.
Stuff floating around, exactly. But these seemingly insignificant particles have a vital role. They act as nuclei for water vapor condensation.
Nuclei. What does that mean?
Think of each dust particle as a tiny little seed, or a magnet maybe. It attracts water vapor, and the vapor condenses around it, forming microscopic water droplets.
So water needs something to grab onto.
It really helps, yes. These tiny droplets then cluster together, enabling the formation of clouds and eventually precipitation like rain or snow.
Wow. So no dust, potentially no rain.
It makes cloud formation much, much harder. So if you sum up the atmosphere's profound importance, oxygen keeps us breathing, carbon dioxide feeds plants, dust particles are essential for rain, water vapor directly influences life, and that tiny bit of ozone shields us from harmful UV rays. It's an incredible system.
It really is. What about its structure? You mentioned layers.
Right, the structure. So the atmosphere extends outwards for about 1,600 kilometers from the surface, but what's surprising is that about 97% of its total mass, its weight essentially, is concentrated within just the first 30 kilometers.
Most of it is really close to the ground then.
Very close, relatively speaking. And we divide this atmosphere into 5 distinct layers, primarily based on how their temperature and density change as you go up. These are the troposphere, stratosphere, mesosphere, ionosphere, and exosphere.
Okay, 5 layers. Let's start at the bottom.
Okay, the troposphere. This is the layer closest to us, the one we live in. Its height isn't uniform, though. It's thickest at the equator, about 18 kilometers, but it thins out significantly towards the poles, down to about 8 kilometers.
Why the difference?
Mostly due to temperature and the rotation of the Earth, causing air to bulge outwards more at the equator. But what makes this layer absolutely crucial is that virtually all of our weather, everything from gentle breezes to violent storms, happens exclusively within the troposphere.
All of it.
All of it. This constant movement and mixing of air, this weather, is vital for the development and sustenance of life down here. The air is always in motion, which is why it's sometimes called the changing sphere.
Okay, and temperature changes too, right?
Yes, generally, as you go higher up in the troposphere, the temperature drops. It decreases at a pretty predictable rate, about 1 degree Celsius for every 165 meters of height gain. We call this the normal lapse rate.
Got it.
The upper boundary of the troposphere is called the tropopause. It's not like a hard ceiling, more like an unstable transition zone that marks the shift into the next layer up.
Which is?
The stratosphere. This sits directly above the troposphere and extends up to about 50 kilometers from the Earth's surface. It has an average thickness of around 40 kilometers.
Okay, and the temperature here?
Well, in the lower part, up to about 20 kilometers, the temperature actually remains quite stable. It doesn't drop much. But here's an interesting twist. Beyond that, the temperature starts to increase with height.
Increase. Why is that?
That warming is directly linked to the presence of that ozone layer we just talked about. The ozone absorbs the sun's ultraviolet radiation, and that energy heats up this part of the stratosphere.
The ozone layers in the stratosphere.
Primarily, yes. And because there are very few weather disturbances here, no clouds, no storms, and the air is remarkably stable, the stratosphere is considered the ideal layer for aircraft to fly in. They get above the weather.
Smoother flying. Makes sense. Okay, what's next?
Beyond the stratosphere, we find the mesosphere. This is the third atmospheric layer, stretching up to about 80 kilometers from the Earth's surface, so it spans about 30 kilometers in thickness.
And the temperature trend here.
Here, temperatures plummet dramatically again. They drop very sharply with altitude, reaching as low as minus 100 degrees Celsius near the top.
Minus 100, that's incredibly cold.
Extremely cold. And this is the fascinating realm where most meteors or shooting stars burn up when they enter Earth's atmosphere. The friction with the sparse air particles at this altitude generates enough heat to vaporize them.
So shooting stars happen in the mesosphere. Cool. Layer 4.
Above the mesosphere lies the ionosphere. This fourth layer extends much higher, up to around 400 kilometers from the Earth's surface, with a width of about 300 kilometers.
Ionosphere. Sounds electric.
It is. The key characteristic here is the presence of electrically charged particles, ions. Solar radiation knocks electrons off gas molecules at this altitude. And this feature is incredibly important for us down here because it's this layer that reflects certain types of radio waves back to Earth.
Like bouncing signals off it.
Exactly. That reflection is precisely what makes long-distance radio broadcasting possible. It allows signals to travel over the horizon.
So crucial for communication.
Very much so.
Yeah.
And finally, the outermost layer is the exosphere. This is situated beyond 400 kilometers above the Earth. It's basically the fringe of the atmosphere merging into space.
What's it like up there?
Well, it's characterized by an extreme scarcity of gas particles. The air is incredibly thin because Earth's gravitational pull is significantly weaker at such high altitudes. Particles can actually escape into space from here.
Wow. So from the very breath we take, the weather we experience, the protection from UV, even the radio waves connecting us, the atmosphere is truly an incredible, intricate marvel.
Absolutely. It directly supports life and our technology in so many ways.
But the Earth itself, the solid ground beneath our feet, it's anything but static, right?
Yeah.
It has this restless core, and that core unleashes powerful forces that we experience really dramatically on the surface.
Indeed. Our understanding of Earth's internal structure reveals it to be fundamentally layered. Think of it like an onion with these concentric layers. There's the crust on the outside, then the mantle, a liquid outer core, and finally a solid inner core right at the center.
And we know this how we can't exactly drill down there.
No, not even close. Our knowledge comes from a fascinating array of indirect evidence. Things like studying Earth's overall size and shape, its density, how it rotates, its gravitational pull, the powerful magnetic field it generates.
The magnetic field comes from the core.
It's generated primarily by the movement within the liquid outer core, yes. We also learn a lot from how seismic waves, the waves from earthquakes, behave as they travel through the planet. They speed up, slow down, or bounce off different layers.
Like an ultrasound for the Earth.
That's a great analogy, yes. And we even get clues from the composition of meteorites, which are thought to be leftover building blocks from when the planets formed, giving us hints about Earth's original ingredients.
So meteorites tell us about Earth's insides.
They provide clues about the overall composition, yeah. It's believed that early Earth was formed from the accumulation of things like meteors and asteroids. Gravitational compression then heated the planet, causing it to melt and differentiate, with the denser materials sinking to the core and lighter materials rising to form the crust. This density sorting created these distinct layers.
So our Earth is this dynamic system. An internally generated magnetic field, a layered interior with solid and liquid bits, and then this crucial gaseous cover, the atmosphere, wrapping it all up.
That's a perfect summary.
Can we dive a bit deeper into those layers, the core, mantle, crust?
Absolutely. Let's start at the center. The core. It's the Earth's densest part, made primarily of iron and nickel. Now, the outer part of the core is liquid, molten metal.
Liquid metal.
Yeah. But the inner core, despite being even hotter, is solid.
How can it be solid if it's hotter?
Immense pressure. The weight of the entire planet pressing down at the center is so vast that it compresses the metals intensely, forcing them into a solid state even at incredibly high temperatures.
Okay, pressure overrides temperature. Got it. What's around the core?
Surrounding the core is the mantle. It's less dense than the core, composed mainly of silicate rocks rich in iron and magnesium. While it's mostly solid rock, the very upper part of the mantle is partially molten, or soft. We call this the asthenosphere. It can flow very slowly over geological time, and the mantle is actually the largest layer of the Earth by volume.
That soft part sounds important.
It is. We'll come back to that. Finally, the outermost layer is the crust. This is what we live on. It's remarkably thin and rigid compared to the other layers.
How thin?
Think of it like the delicate skin of an apple compared to the flesh inside. The crust makes up only about 1% of Earth's total mass. It's incredibly thin.
Just 1%, that's tiny.
Relatively, yes. And we distinguish between two types. Continental crust, which makes up the land masses, is generally thicker and less dense, composed mainly of rocks like granite. Then there's oceanic crust, which lies beneath the oceans. It's thinner but denser, made mostly of basalt.
Granite and basalt, okay.
And yeah, as we mentioned, our insights into this whole internal layout come from combining density calculations, meteorite studies, and crucially, analyzing how those seismic waves travel. The way they bend and reflect tells us where the boundaries between these layers are.
That's fascinating, thinking about the Earth's crust as being as thin as an apple's skin. And here's where it gets really interesting for us up here on the surface. The idea that this thin skin, the Earth's surface, isn't one solid piece. It's like a giant jigsaw puzzle, right?
Yeah.
Made of constantly moving plates.
Exactly. This brings us directly to the theory of plate tectonics. This concept, which really solidified in the 1960s, completely revolutionized geology. It explains how the Earth's outer film, this rigid layer called lithosphere, moves and deforms.
Lithosphere. That's the crust plus.
Plus the very uppermost rigid part of the mantle. So the crust and a bit of the solid mantle beneath it act together as a rigid plate.
Okay.
And plate tectonics provides this incredibly powerful framework that helps us predict and explain almost every major geological event and feature we see on the Earth's surface. Mountains, earthquakes, volcanoes, ocean basins.
It explains all that.
It's the unifying theory, yes. So what exactly is a plate? Simply put, it's a rigid piece of this lithosphere, and it's defined by boundaries on all sides. It's like a giant, irregularly shaped slab.
Okay.
We generally talk about two broad types: oceanic plates, which lie beneath the oceans, and continental plates found beneath the continents, although many plates contain both types of crust.
Right.
And where continents meet oceans, we have continental margins. Some of these are active margins, meaning they are plate boundaries where things are happening, collisions, sliding. Others are passive margins, which are not active plate boundaries. They're just where the continent transitions into the ocean within the same plate.
Got it. Active versus passive.
Yeah. And the Earth's entire exterior, this lithosphere, is fractured into about 12 major plates plus several smaller minor plates. And they are constantly in motion, gliding across the top of that softer, partially molten mantle layer beneath them, the asthenosphere we mentioned.
Floating on the mantle almost.
It's a good way to think about it, yeah, like giant rafts on a very, very slow-moving river. These plates are always moving in different directions, at different speeds, typically a few centimeters per year, about the rate your fingernails grow.
How slow?
Seems slow to us, but over millions of years, it adds up to continents moving thousands of kilometers. And this movement causes them to interact at their boundaries. They can collide, pull apart, or scrape past one another.
Okay, the interactions are key.
Absolutely. Each type of interaction creates a distinct set of geological features and events. The word tectonic itself directly refers to the deformation of the Earth's crust that results from these plate interactions. It truly is like the Earth's surface is broken into this colossal jigsaw puzzle, and plate tectonics describes the dynamic movement of these pieces.
So who are the major players, the big plates?
Well, we have several very large major plates. There's the Pacific Plate, the largest, the North American Plate, the South American Plate, the Eurasian Plate, the African Plate, and the Australian Indian Plate, sometimes considered two separate plates.
Okay, and minor ones too.
Yes, numerous minor plates which are smaller to moderate in size. Examples include the Juan de Fuca Plate off the U.S. Pacific Northwest, the Cocos Plate off Central America, the Caribbean Plate, the Scotia Plate near Antarctica, the Arabian Plate, and the Nazca Plate off Western South America, among others. They all fit together in this complex global system.
Right, it's a global puzzle.
It is. And the interactions between these plates give rise to some of Earth's most dramatic geological features. For example, mid-ocean ridges. These are colossal underwater mountain ranges that form where plates are pulling apart.
Under the sea.
Yes, stretching for thousands of kilometers along the ocean floor. Imagine vast submarine mountains where new ocean floor is being continuously created as magma rises up.
Wow. What else?
A trench, an oceanic trench, is a very deep, elongated trough in the ocean floor. These mark where one plate is diving or subducting beneath another plate. The Mariana Trench is the most famous example.
The deepest parts of the ocean.
Exactly. The ridge axis is simply the very summit, the center line of a mid-ocean ridge. It pinpoints the exact location where new crust is actively forming at that divergent boundary.
Okay.
A fracture zone is a linear band of cracks and faults on the ocean floor, often running perpendicular to mid-ocean ridges. These accommodate the sideways motion as sections of the ridge spread at different rates. The actively sliding part is called a transform fault.
Like a tear in the ocean floor?
Sort of, yeah, accommodating differential movement. And finally, a volcanic arc. This is a curving chain of active volcanoes that forms parallel to a convergent plate boundary, where one plate is subducting beneath another. The Andes Mountains are a classic example on a continent.
So volcanoes line up along these boundaries.
Very often, yes. And what moves these plates? It's believed to be driven by mantle convection cells. Think of it like a giant pot of very thick soup simmering on a stove. Hot material from deep within the earth rises, spreads out beneath the plates, cools, and then sinks back down. This slow circulation drags the lithospheric plates along like they're riding on top of these currents.
The conveyor belt idea again?
Exactly. And plate boundaries are clearly recognizable because they are the zones where most earthquakes occur and where many volcanoes are found. The interiors of the plates are generally much more stable, with far fewer seismic events.
Makes sense.
Yeah.
So what are the main types of boundaries? You mentioned pulling apart, colliding.
Right. There are three primary types of plate boundaries, each with its own unique geological story.
Okay.
First, divergent plate boundaries. This is where plates move away from each other. Mid-ocean ridges are the classic example. This is the birthplace of new oceanic lithosphere.
Creating new crust.
Precisely. What happens is hot mantle material wells up beneath the ridge, melts due to the reduced pressure, and then erupts as basaltic magma right at the ridge axis. This magma cools and solidifies to form new oceanic crust.
Okay.
This newly formed crust is then continuously pushed or pulled aside as more magma erupts, meaning the further you move away from the ridge crust, the older the oceanic crust becomes.
The Atlantic Ocean is getting wider.
Yes, very slowly. Because of the mid-Atlantic ridge. Interestingly, because oceanic lithosphere eventually gets recycled back into the mantle at subduction zones, the ocean basins themselves are comparatively young in geological terms. The oldest oceanic crust we've found is only from the Jurassic period, about 180 million years old, found off the coast of Japan. Continents are much older.
Wow, only Jurassic. That's young for geology.
Relatively speaking, yes. And because the ridges are zones of young crust, there's very little sediment accumulated right on them. But as the crust moves away and gets older, sediment thickness steadily increases. The speed at which the plates pull apart the spreading rate also affects the landscape. If plates spread quickly, like at the East Pacific Rise, more hot magma rises, creating broader, less rugged undersea mountains and often lacking a deep central rift valley. Where spreading is slow, like the Mid-Atlantic Ridge, the ridge is typically narrower, more rugged, and has a prominent rift valley down the center.
Interesting.
And as this newly formed oceanic lithosphere moves away from the heat of the ridge, it cools down, becomes denser, and contracts. This causes it to sink deeper into the underlying asthenosphere. So the ocean floor generally gets progressively deeper the further away you get from the mid-ocean ridge.
Okay, that explains ocean depth patterns. What's the second type of boundary?
Second, we have convergent plate boundaries. This is where plates move toward each other. They collide.
Head-on collision.
Head-on, or sometimes at an angle. What happens next depends on the types of crust involved. If a denser oceanic plate collides with another plate, either oceanic or continental, the denser oceanic plate will subduct. That means it dives down beneath the other plate and sinks back into the mantle.
The heavier one goes under.
Exactly. This process creates those deep oceanic trenches on the seafloor, marking the line of subduction. This whole area is called a subduction zone.
Okay.
Now, as the oceanic plate descends deeper into the mantle, it heats up. Also, water trapped in the minerals of the subducting plate gets released. This water rises into the overlying mantle wedge, and crucially, water lowers the melting point of the mantle rock.
Water makes rock melt easier.
At those temperatures and pressures, yes. So the mantle rock above the subducting plate begins to melt, forming magma. This buoyant magma then rises towards the surface.
Then forms volcanoes.
Precisely. It erupts, creating a chain of volcanoes known as a volcanic arc that runs parallel to the oceanic trench on the overriding plate. If the subduction occurs beneath continental crust, you get a continental volcanic arc, like the Andes. If it happens beneath another oceanic plate, you get an island volcanic arc, like Japan or the Aleutian Islands.
Got it. So subduction causes volcanoes.
Yes. And since oceanic lithosphere is always denser than continental lithosphere, if a plate carrying continental crust collides with an oceanic plate, the oceanic plate will always be the one to subduct. If two continents collide, neither wants to subduct fully, so they crumple up and form huge mountain ranges, like the Himalayas.
That's how mountains like the Himalayas form.
It's the mechanism, yes. Continent collision. One other feature here. Sediments scraped off the subducting oceanic plate, plus bits of the overriding plate, get intensely folded and faulted, piling up in the trench area. This chaotic jumble of rock is known as an accretionary prism or accretionary wedge.
Okay, a lot happens at convergent boundaries. What's the third type?
The third type is transform plate boundaries. Here, lithospheric plates simply slide horizontally past one another. There's no creation of new crust, like at divergent boundaries, and no destruction of crust, like at convergent boundaries.
Just sliding sideways.
We're sliding sideways along a large fault called a transform fault. The San Andreas Fault in California is probably the most famous example of a transform boundary.
Right. Lots of earthquakes there.
Exactly. Earthquakes along these transform faults are very common, but they're typically shallow focus earthquakes, meaning they originate relatively close to the Earth's surface because the plates are only sliding past each other in the upper brittle part of the lithosphere.
Okay. Shallow, but potentially powerful.
Definitely.
It's truly astounding to think about these massive pieces of our planet's surface constantly grinding against, pulling apart from, or sliding past each other. And the most dramatic, often terrifying manifestation of these relentless movements, the one we often hear about in the news, is an earthquake.
That's right. Earthquakes are essentially the Earth's sudden, sometimes incredibly violent, way of releasing the immense stress that builds up along these plate boundaries or other faults due to that constant movement.
The ground suddenly breaking.
Exactly. Let's look at their general characteristics. Earthquake vibrations, or seismic waves, ripple through the Earth at different frequencies and speeds. The actual rupture itself, the moment the ground breaks along the fault, for a major earthquake might only last from a few seconds up to perhaps a minute. But the seismic waves generated by that rupture can continue to shake the ground for several minutes afterwards.
Okay. And they start deep down.
They can originate at different depths. The depth of the focus, or hypocenter, where the earthquake rupture begins, is incredibly important. We classify them based on this depth. Earthquakes can be deep focus, originating between 300 and 700 kilometers down.
That's really deep.
Very deep, yeah, usually associated with subducting plates plunging deep into the mantle. Then there are intermediate focus earthquakes, between 60 and 300 kilometers deep. And finally, shallow focus earthquakes, which originate less than 60 kilometers below the surface.
And the shallow ones are worse.
Generally, yes, for surface damage. Deep focus earthquakes, while they can be powerful, rarely cause significant damage at the surface because their energy has dissipated considerably over the large distance it travels to reach us. In stark contrast, shallow focus earthquakes, even if they release the same amount of energy, can be far more devastating simply because they happen much closer to the surface where people and buildings are. And they are also the most common type.
Right. Proximity matters. How do we measure them? The Richter scale.
Yes, the Richter magnitude scale is the one most people have heard of, although seismologists now often use the moment magnitude scale, no W, which is more accurate, especially for large quakes. But the principle is similar. Magnitude scales quantify the amount of energy released by the earthquake.
How does it work?
It's measured using a seismograph, an instrument that detects and records the ground's vibrations. Charles Richter developed his scale back in the 1930s. It mathematically adjusts the readings based on the amplitude, the size of the recorded seismic waves, correcting for the distance between the seismograph and the earthquake's origin point, the epicenter, the point on the surface directly above the focus.
Okay.
What's absolutely crucial to understand about magnitude scales like Richter is their logarithmic nature. This means that each whole number increase in magnitude represents a 10-fold increase in the measured amplitude of the ground motion recorded by the seismograph.
10 times bigger shaking for each number up.
10 times bigger ground motion, yes. And perhaps even more importantly, each whole number increase corresponds to roughly 30 times more energy being released by the earthquake.
30 times more energy.
Roughly, yes. So for example, a magnitude 7.5 earthquake isn't just slightly stronger than a 6.5, it releases about 30 times more energy. And compared to a 5.5, that 7.5 releases about 30 times 30, which is 900 times more energy.
Wow, that difference really scales up fast.
It really does. To give you some context, an earthquake of magnitude 3 is typically the smallest that a human can actually feel. Anything smaller is usually only detected by sensitive instruments.
Okay. Can you give us a sense of the effects at different magnitudes?
Sure. Let's consider the typical effects based on the Richter scale, although local conditions can modify these quite a bit. Below 3.5. Generally not felt by people, but it is recorded by seismographs. Millions of these happen every year. 3.5 to 5.4. Often felt, but usually causes only minor damage, if any. Maybe rattles dishes or cracks plaster. Around 5.5 to 6.0 can cause slight damage to well-designed buildings, but potentially major damage to poorly constructed structures, especially in localized areas close to the epicenter. 6.1 to 6.9 can be destructive in populated areas, causing significant damage up to about 100 kilometers across. 7.0 to 7.9. This is considered a major earthquake, capable of causing widespread and serious damage over much larger regions. 8.0 or greater. A great earthquake can cause catastrophic destruction and serious damage across areas several hundred kilometers across. Think of the 2004 Indian Ocean quake or the 2011 Japan quake.
So the potential for damage really skyrockets at the higher magnitude.
Absolutely. Now, the most immediate and dangerous hazards directly from an earthquake are fault displacement, the ground actually breaking and shifting and ground shaking. Fault displacement, whether it's a slow creep over time or a sudden rupture during the quake, can directly damage building foundations, roads, pipelines, or physically shift the land, creating scarps, cliffs, or troughs. But it's usually localized right along a fault line.
Right.
However, it's the ground shaking the vibration spreading out from the earthquake that typically causes the most widespread devastation, particularly to buildings and infrastructure, the human-built environment.
What affects how bad the shaking damage is?
Several factors. Obviously, the earthquake's magnitude. More energy means stronger shaking. Its depth, shallower, means more intense shaking at the surface. The distance from the epicenter, but also the type of local geology. Soft soils and sediments can actually amplify shaking compared to solid bedrock. And of course, the type and quality of building construction is critical. Poorly built structures are far more vulnerable.
Building codes matter.
Hugely. And it's also really important to remember aftershocks. These are smaller earthquakes that often follow the main quake for days, weeks, or even months. They can cause significant further damage to buildings already weakened by the main shock, and they really hinder rescue and recovery efforts.
Right. The danger isn't over when the main shaking stops.
Not at all. Beyond the direct shaking and fault rupture, earthquakes can trigger numerous secondary hazards. Things like ground collapse or settlement, liquefaction where water-saturated soil temporarily loses its strength and behaves like a liquid.
Buildings can sink or tilt.
Exactly. Also, landslides and rockfalls, especially in hilly or mountainous areas, snow avalanches in colder regions. And if the earthquake occurs under the ocean or displaces water in a large lake, it can generate devastating tsunamis.
Giant waves.
Giant waves, exactly. So the impacts ripple outwards.
Let's talk more about those broader impacts, maybe focusing on the ground shaking.
Yeah.
What kind of damage does it cause?
Well, in terms of physical damage, it's extensive. It affects homes, people's belongings. Critical infrastructure takes a massive hit. Bridges collapse, elevated roads fail, railway lines get buckled, water dams can be breached, water treatment plants damaged, utility lines, gas, water, electricity severed, pipelines broken, electrical generating stations and transformers destroyed.
A total breakdown of services.
Pretty much. And this can trigger further secondary effects like widespread fires, often from broken gas lines, dam failures leading to flooding, and landslides that might even block waterways, causing further flooding upstream. Damage to facilities handling hazardous materials is also a major concern, potentially leading to dangerous spills. The destruction of property leads to massive shelter needs, disrupts economic production, lowers living standards, and causes widespread homelessness.
Devastating. What about health impacts?
From a public health perspective, aside from the immediate deaths, fracture injuries, broken bones are often the most universal problem, overwhelming local medical facilities. A breakdown in sanitation due to damaged water and sewage systems can lead to fears of disease outbreaks, especially if public health control measures fail in the chaotic aftermath. Existing endemic diseases could become epidemics, and the psychological consequences, trauma, anxiety, depression from injury, loss, and fear can linger for months or even years.
Long-term mental health effects, too.
Definitely. Water supply is almost always severely disrupted. Supply lines break, distribution systems fail, storage tanks crack, Dams are damaged, even open wells can be blocked or contaminated. Earthquakes can even permanently alter groundwater levels, sometimes causing wells or springs to dry up completely.
Essential services gone.
Completely disrupted. The transport network is often crippled, roads fail, bridges are down, flyovers collapse, railway line alignments get warped, airport runways might be damaged and unusable. Getting aid in and people out becomes incredibly difficult. Yes. Similarly, electricity and communication links are usually severed. Power lines fall, towers collapse, transponders and transformers crumble. Everything goes dark and silent.
And food.
Food supplies can see initial disruption in supply and marketing systems due to transport failures. Irrigation systems might be damaged, affecting future crops. If significant flooding or a tsunami occurs, existing food stocks or crops near the coast could be lost. However, typically, the earthquake itself doesn't drastically reduce the overall local food supply in the long run unless agricultural infrastructure is very severely damaged.
Okay.
So if we connect this all back to the bigger picture, you can really see how deeply interconnected these seemingly separate things are. The movement deep within the earth triggers an event on the surface, and the impacts of that event ripple through every aspect of human society, infrastructure, health, economy, daily life.
It's a powerful and sobering reminder of the forces at play beneath us. That interconnectedness is truly striking. We've talked about the Earth's deep layers, its restless core, the dramatic forces it unleashes. But what about the very stuff it's made of? The solid materials that compose its crust? Thinking about them as like the fundamental building blocks, the Earth's very foundation.
Precisely. And those building blocks are, of course, rocks. To put it simply, as geologists Ehlers and Blatt did, rocks are the stuff the Earth is made of.
Can't get simpler than that.
Right. A slightly more scientific definition is that a rock is a naturally occurring, solid, cohesive aggregate, meaning stuck together of one or more minerals or mineral-like materials.
Okay, collections of minerals.
Essentially, yes. And based on how they form, rocks are primarily categorized into three major groups: igneous rocks, sedimentary rocks, and metamorphic rocks.
The three big families. Let's start with igneous. Sounds fiery.
It is. The name comes from the Latin word ignis, meaning fire, which perfectly captures their origin. Igneous rocks form from the cooling and solidification or crystallization of molten rock. We call this molten rock magma when it's underground, and lava when it erupts onto the surface.
Okay, cooled from hot liquid. Where does the magma come from?
It originates from the partial melting of existing rocks deep within Earth's mantle, or sometimes the lower crust. Rocks melt down there due to a few main reasons: a significant rise in temperature, a reduction in pressure, which lowers the melting point, or a change in their chemical composition, like adding water, which we saw in subduction zones.
Right, the water trick.
Exactly. And the distribution of different types of igneous rocks across the globe is significantly influenced by plate tectonics. It really explains why we find certain rocks in certain places.
Like what?
For instance, at divergent plate boundaries, those mid-ocean ridges where plates pull apart, the upwelling mantle melts to produce basaltic magma, forming rocks like basalt and its coarser-grained equivalent, gabbro. This makes up virtually all of the oceanic crust.
Okay, basalt at spreading centers.
Right. In contrast, at convergent plate boundaries, especially where subduction occurs under continents, the melting processes are more complex and tend to produce magmas that are richer in silica, leading to rocks like andesite, dacite, rhyolite, and their intrusive equivalents like diorite and granite. Think of the Andes or the Cascade Range.
So different plate settings, different igneous rocks.
Broadly speaking, yes. We also subdivide igneous rocks based on where they cool and solidify. If the magma cools very slowly deep inside the Earth's crust, it allows large mineral crystals to grow. These are called plutonic or intrusive rocks. Granite is the classic example. You can often see the individual mineral grains quite easily.
Okay, cooled slowly underground.
Then you have volcanic or extrusive rocks. These form when magma erupts onto the Earth's surface as lava or is violently ejected as ash and fragments. Pyroclastics. Because they cool very quickly in contact with air or water, there's little time for large crystals to form. They are typically fine-grained or even glassy. Basalt lava flows are a common example, or pumice, which is frothy volcanic glass.
Cooled quickly on the surface. Got it.
And the specific sequence in which different minerals crystallize from a cooling magma is described by something called Bowen's reaction series. It's a fundamental concept in geology that helps explain the diverse mineral compositions and textures we see in igneous rocks, based on things like the magma's chemistry and its cooling rate.
Okay, complex chemistry involved. What about the second family, sedimentary rocks?
Right, sedimentary rocks. These are fascinating because although they often form relatively thin layers right at or near the Earth's surface, they actually make up a huge proportion of the rocks exposed on land and cover most of the ocean floor. One estimate suggests they constitute about 66% of the Earth's crust by volume, though other estimates put it lower, focusing just on surface exposure.
So they're very common on the surface.
Very common on the surface, yes. They are formed from the accumulation and cementation of sediments. Sediments are basically fragments of pre-existing rocks, igneous, metamorphic, or older sedimentary rocks that have been broken down by weathering, or they can be mineral crystals that precipitate out of water, or even the remains of living organisms like shells.
Broken bits, chemical precipitates, or fossils.
Exactly. These sediments are transported by wind, water, or ice, eventually deposited in layers like in oceans, lakes, or deserts, and then over time they get buried, compacted by the weight above, and cemented together by minerals precipitating from groundwater. This whole process is called lithification.
Turning loose sediment into solid rock.
Precisely. And because of how they form, sedimentary rocks often contain clues about past environments, fossils, ripple marks, mud cracks. They tell stories about Earth's history. We further classify them based on the type of sediment. Clastic, made of broken rock fragments like sandstone or shale. Chemical, precipitated from water like rock salt or some limestones. And organic or biochemical, made from organic remains like coal or fossiliferous limestone.
Okay, different types based on the ingredients. And the third type, metamorphic.
Metamorphic rocks. The name comes from meta, meaning change, and morph, meaning form. So these are rocks that have changed form. They are essentially existing rocks. They could start as igneous, sedimentary, or even older metamorphic rocks that have been transformed by intense heat, intense pressure, or the action of hot fluids deep within the earth.
Changed by heat and pressure. Where does this happen?
Usually deep underground, often associated with mountain building processes at convergent plate boundaries, or where magma intrudes into existing rock, baking it. The key is that the changes happen without the rock melting. If it melts, it becomes magma and will form an igneous rock upon cooling. Metamorphism happens in the solid state.
So it changes, but doesn't melt.
Exactly. The original rock before metamorphism is called the protolith. During metamorphism, the minerals within the protolith can recrystallize, forming new minerals that are stable under the new high-temperature, high-pressure conditions. The texture of the rock also changes, often developing layers or bands called foliation, like you see in slate or gneiss.
Foliation, like stripes.
Kind of like stripes or parallel alignment of mineral grains. Yeah, caused by directed pressure. In low-grade metamorphism, lower temperatures and pressures, you can sometimes still see features of the original protolith, which helps geologists figure out what the rock used to be. But as the grade of metamorphism increases, higher temperature and pressures, the original textures are often completely obliterated and replaced by new metamorphic ones. Then geologists have to rely more on the rock's overall chemical composition to deduce its origin.
So it can be hard to tell what it was before.
Sometimes, yes, especially with very high-grade metamorphism.
Okay. So these different rock types, igneous, sedimentary, metamorphic, they aren't just sitting there in isolation, are they? You mentioned they change form. They're constantly transforming through something truly remarkable called the rock cycle. It's like Earth's own incredibly patient and continuous recycling program.
That's a perfect analogy. The rock cycle describes this continuous sequence of events involving the formation, alteration, destruction, and reformation of rocks through Earth's natural processes. It beautifully illustrates how all three main classes of rocks are profoundly interconnected, constantly changing from one form to another over vast stretches of geological time.
It connects everything together.
It really does. It shows there's no real beginning or end. Any rock can become any other type of rock given the right conditions and enough time.
Can you trace some of those transformations for us? How does it work?
Sure. Let's start with any rock on the Earth's surface, say an igneous rock like granite that's exposed in a mountain range.
Okay, Granite Mountain.
First, it gets weathered. Physical weathering like frost wedging or abrasion breaks it into smaller pieces. Chemical weathering like rainwater, which is slightly acidic, starts dissolving some minerals and altering others. This granite might break down into tiny particles of clay. from feldspar minerals, and grains of sand, mostly quartz.
Okay, breaking down.
These sediments, the clay and sand, are then eroded and transported, maybe by rivers, downhill towards the sea. Eventually, the river slows down, and the sediments get deposited in layers, maybe in an ocean basin.
Dropped off at the bottom.
Right. Over time, more and more sediment piles on top. The weight compacts the lower layers, squeezing water out. Minerals dissolved in the remaining water then precipitate between the grains, cementing them together. This process, lithification, turns the loose sediments into solid sedimentary rock. The clay might become shale, and the sand might become sandstone.
So igneous granite became sedimentary shale and sandstone.
Exactly. Now, what could happen to that shale or sandstone? Well, maybe tectonic forces bury it deeper and deeper within the earth.
Okay, gets pushed down.
As it gets buried, both temperature and pressure increase significantly. If they get high enough, the shale or sandstone will undergo metamorphism. The minerals will change, recrystallize, maybe develop that foliation we talked about. The shale could transform into slate, then perhaps phyllite, then schist, then gneiss with increasing metamorphic grade. The sandstone, which is mostly quartz, might transform into a very hard metamorphic rock called quartzite.
So sedimentary rock became metamorphic rock.
Correct. Now, what if the temperature and pressure get even higher? If our metamorphic gneiss or quartzite gets pushed deep enough or comes into contact with magma,
It melts.
it melts. It turns back into magma.
Ah, back to the beginning, sort of.
Exactly. And if that magma eventually finds its way towards the surface, maybe erupts from a volcano, it will cool and solidify to form a new igneous rock, maybe rhyolite if it erupted, or granite if it cooled underground. And the whole cycle can start over again. And remember, any rock type can take shortcuts. That surface granite could get buried and metamorphosed directly into gneiss without becoming sediment first. The sedimentary shale could be uplifted and weathered back into sediment without becoming metamorphic. The metamorphic quartzite could be uplifted and weathered. Magma could cool underground as granite, never erupting, then be uplifted and weathered. It's a complex web of interconnected pathways.
It truly is Earth's great transformation machine, constantly recycling its own materials.
Over millions and millions of years, yes.
Incredible. We've explored the solid Earth, its deep structure, its restless plates, the rocks it's made of, and even its fiery heart with magma. Now let's pivot back upwards, back to how the atmosphere itself organizes, moves, and creates the weather we experience every day. It's time to talk more about the dance of air and water, maybe starting with these things called air masses.
Right, air masses. These are fascinating because they are essentially vast bodies of air, often covering thousands of square kilometers, that maintain relatively uniform temperature and humidity properties horizontally. Think of them as huge, coherent blobs of air.
Uniform blobs.
Pretty much, yeah. At least horizontally. Their specific characteristics, whether they're warm or cold, moist or dry, are determined by the region where they originate, which we call the source region.
Okay, so where they come from matters most.
Exactly. An air mass sits over its source region for several days, sometimes weeks, and takes on the temperature and moisture characteristics of that surface. For a source region to be effective, it needs to have fairly uniform surface conditions, like a large ocean area, a vast desert, or a snow-covered plain, and relatively light winds, allowing the air to stagnate and acquire those properties.
Where do these usually form?
Good source regions are typically found only in high latitudes, like polar regions, or low latitudes, like tropical oceans or deserts.
Yeah.
The middle latitudes, where we live, tend to have weather systems moving through too quickly and too much variability for large, stable air masses to truly form there, although they certainly move through the mid-latitudes.
Okay, high or low latitudes.
And when these air masses eventually move away from their source regions, they bring their distinct characteristics with them. They displace the local air that was there before, causing significant changes in temperature and humidity wherever they travel. This movement of air masses is a primary driver of weather changes in the mid-latitudes.
Ah, so a cold front is basically one air mass pushing at another.
Essentially, yes.
Okay.
A front is the boundary between two different air masses.
Okay, how are they classified? You mentioned warm, cold, moist, dry.
Right. We classify air masses based on those two main characteristics of their source regions, moisture content and temperature. For moisture, they are either continental, designated with a small c, meaning they formed over land and are therefore dry, or maritime, small m, meaning they formed over water and are moist.
C for dry, M for moist. Got it.
Then for temperature, which primarily reflects the latitude of the source region, they can be tropical, designated with a capital T, meaning warm or hot, Polar, capital P, meaning cold, or Arctic, capital A, meaning extremely cold.
T for tropical, P for polar, A for Arctic. Okay.
So we combine these using a simple two-letter naming convention. A small letter for moisture, followed by a capital letter for temperature. For example, CP means continental polar air, dry and cold. MT means maritime tropical air, moist and warm.
Makes sense. So how many types are there? CT, CP, CA, MT, MP, MA? 6.
Logically, yes, you'd expect 6 combinations. However, the maritime Arctic, MA type, forming over Arctic oceans, isn't usually considered a distinct category because the Arctic oceans are often ice-covered, making the air above them functionally similar to continental Arctic air, very cold and dry. So, we generally talk about 5 main types that significantly affect weather, particularly in places like North America.
Okay, 5 main types. Can we run through them quickly?
Sure. Let's start with continental polar, CP. These air masses form over vast high-latitude land masses like northern Canada or Siberia, especially in winter. They are notably cold and extremely dry. Because the ground is cold and often snow-covered, the air near the surface gets very cold too, making the atmosphere very stable. This stability means you get very few clouds within a CP air mass, often leading to clear, cold days.
The crisp, cold winter air.
Exactly. As these CP air masses move southwards into lower latitudes, they start to warm up from contact with the warmer ground. This warming increases their capacity to hold moisture, though they start very dry, and decreases their stability somewhat, maybe leading to some fair weather cumulus clouds, but they still bring those characteristic cold snaps.
Okay. What about CA, continental Arctic?
Continental Arctic, CA, is like CP, but even more extreme. It forms over the very coldest ice and snow-covered regions of the Arctic in winter. This air is incredibly cold and contains virtually no water vapor simply because it's too cold to hold any significant moisture. The boundary between CA and the slightly less cold CP air is often a sharp temperature contrast known as the deep Arctic front. When CA air masses plunge south, they deliver the most severe cold waves, sometimes reaching as far south as the Gulf Coast of the U.S.
The real deep freeze, got it. What about the warm, dry one, CT?
Right, continental tropical CT. In North America, this air mass forms primarily over the desert regions of the U.S. Southwest and northern Mexico, mainly during the summer months. It's characterized by being very hot and very dry. Although the intense surface heating makes this air inherently unstable, clear skies usually prevail simply because there's so little water vapor available to form clouds.
Hot and dry desert air.
Exactly. However, if some moisture gets drawn into the CT air mass, perhaps from the Gulf of Mexico or the Pacific, or if the air is forced to rise over mountains or norographic lifting, the instability can trigger thunderstorms, sometimes intense ones despite the overall dryness.
Okay, now the maritime ones, moist air.
Yes, let's do maritime polar, MP, first. These air masses originate over the cool, high-latitude oceanic regions, like the North Atlantic or North Pacific Oceans. So they're cool and moist. Interestingly, MP air often starts its life as CP air that moves out from the continents over the ocean. The relatively warmer ocean water adds heat and, crucially, moisture to the lowest layers of the air mass.
So CP becomes MP over the ocean.
Often, yes. Along the U.S. West Coast, MP air masses moving in from the Pacific bring cool, damp, often overcast conditions, especially in winter, sometimes with prolonged periods of rain or drizzle, particularly when lifted by coastal mountains. On the U.S. East Coast, MP air often affects the region after a winter storm cyclone has passed, bringing chilly, damp weather with winds off the Atlantic.
Okay, cool and damp. What's the last one? MT.
Finally, maritime tropical, MT. These air masses form over warm, low-latitude oceans, like the Gulf of Mexico, the Caribbean Sea, and the subtropical Atlantic and Pacific. As you'd expect, they are very warm, very humid, and often unstable, especially in their lower layers.
Warm and muggy.
Exactly. Those MT air masses originating from the Atlantic and Gulf of Mexico are the primary source of moisture for precipitation across the entire eastern two-thirds of the United States. In summer, as this warm, humid air flows northward over the even hotter continent, the combination of high temperature and high humidity can become dangerously oppressive, thinky heat waves.
Summer misery sometimes.
It can be, yeah. MT air masses also significantly influence the weather in the southwestern U.S., particularly during the summer months, contributing to the North American monsoon phenomenon there, bringing thunderstorms to the desert regions.
So these massive, distinct bodies of air really dictate our regional weather patterns as they move around.
They are fundamental building blocks of weather systems, absolutely.
But some air movements are even more dramatic and predictable on a larger seasonal scale. This brings us to a truly powerful and globally significant wind system, the monsoon winds.
Ah, yes, the monsoon. The term itself describes this powerful seasonal reversal of wind patterns, and it's most famously and perhaps most dramatically exemplified over India and Southeast Asia, although monsoon-like systems exist elsewhere too.
Seasonal wind reversal, what does that mean exactly?
It means the prevailing wind direction flips by almost 180 degrees between seasons, typically between summer and winter. Over India, for instance, the winds blow predominantly from the southwest for about half the year, the summer monsoon period, and from the northeast for the other half, the winter monsoon period.
Okay, a total flip in direction.
Yes, and this wind shift brings profound changes in weather, especially rainfall. The southwest monsoon, which typically lasts from June to September, is the famous one. It brings immense amounts of moisture picked up from the warm tropical Indian Ocean inland over the Indian subcontinent, delivering the vast majority, often 70–80% of India's total annual rainfall during just those few months.
So summer is the wet season.
Very much so.
Oh.
In contrast, the winter or northeast monsoon, generally from about October to December, involves drier air flowing from the continent towards the ocean. While it does bring some significant rainfall to the southeastern coast of India, like Tamil Nadu, it contributes a much smaller amount to the overall yearly precipitation for most of the country.
Okay, what's particularly notable about the summer monsoon?
Well, two features are really striking. First, its remarkable consistency in occurrence. It reliably happens every year, generally arriving around the beginning of June and retreating by the end of September. But second, and critically, is the highly unpredictable variation in the total amount of rainfall it delivers from one year to the next.
Unpredictable rainfall.
Highly unpredictable. We see clear examples of years with devastating floods, signifying an unusually strong or wet monsoon, or years with severe droughts, indicating a weak or dry monsoon, where India receives either far too much or far too little seasonal rainfall compared to the average.
Huge swings from year to year.
Huge swings. And even within a single monsoon season, there's significant variability. This is often called intraseasonal variability. It's marked by distinct active periods, lasting maybe a week or two, with widespread heavy rainfall, followed by break periods, also lasting days or weeks, with very little or no rainfall, especially over central India and the west coast.
Active and break phases.
Exactly. And this year-to-year variability, interannual, and the within-season active break cycles have an absolutely enormous socioeconomic impact on India and surrounding regions. Agriculture is deeply dependent on the monsoon rains, so its timing and intensity affect food security for hundreds of millions. Public health, water resources, energy production, they are all profoundly linked to the monsoon's behavior.
Lives and livelihoods depend on it. What causes this dramatic seasonal wind reversal?
The fundamental driver is the large-scale temperature contrast that develops between the vast Asian landmass and the surrounding Indian Ocean. Land heats up and cools down much faster than water.
Right, we talked about that with air masses.
Exactly the same principle, but on a continental scale. During the spring and early summer, April-May, the intense solar heating warms the Indian subcontinent significantly. This creates a broad area of low atmospheric pressure over the land. Meanwhile, the Indian Ocean remains relatively cooler, maintaining higher pressure.
Low pressure over land, high pressure over sea.
Right. Air naturally flows from high pressure to low pressure. So moist air from over the southern Indian Ocean begins to flow towards the low pressure over land.
Yeah.
As this air crosses the equator, the Earth's rotation, the Coriolis effect, deflects it to the right in the northern hemisphere, turning it into a southwesterly wind flowing over India. This is the onset of the southwest monsoon.
Ah, the wind gets bent by rotation.
Correct. This incoming moist air rises as it encounters the heated land and the mountains, like the Western Ghats and the Himalayas, leading to widespread cloud formation and the characteristic heavy monsoon rainfall. This whole low-pressure zone over northern India is often referred to as the monsoon trough.
Okay, and the daily rain comes from?
The day-to-day rainfall during the monsoon season isn't usually just a steady drizzle. It's often associated with specific weather disturbances embedded within the overall monsoon flow. These can range in intensity from relatively weak, low-pressure systems to stronger monsoon depressions and occasionally even tropical cyclones that form over the Bay of Bengal and move inland. These systems enhance the convergence of moist air and upward motion, leading to concentrated heavy rainfall.
So storms within the monsoon.
Yes. And those active and break periods we mentioned are believed to be connected to the north-south fluctuations in the position of the monsoon trough over India, and also linked to the formation, intensity, and track of these monsoon disturbances within the trough.
It's a complex system.
Incredibly complex. Forecasting monsoon rainfall, both the seasonal total and the active break spells, is therefore crucially important for India and the entire region, and by extension for the global economy and climate system due to the monsoon's vast influence.
I can imagine forecasting is a huge challenge.
It is. With advances in weather and climate prediction models, accurately simulating and predicting the monsoon's intricate behavior remains a major focus of research worldwide. There's ongoing debate about how much of the monsoon's variability is predictable based on slowly changing factors like sea surface temperatures in the Pacific and Indian Oceans, like El Niño effects, or snow cover over Eurasia, versus how much is due to the complex internal dynamics and inherent chaotic nature of the atmosphere itself.
Nature versus nurture for the monsoon, almost.
Kind of, yeah. Boundary forcing versus internal variability.
How long have we understood monsoons?
Well, the phenomenon itself is ancient. People have lived with it for millennia, but its precise scientific nature has only been unraveled relatively recently, although meteorologists and others have been studying its complexities for centuries, going back to traders using the seasonal wind shifts. As our understanding grew, the definitions evolved.
How do we define it now?
Well, simply put, a monsoon is a seasonal reversing wind system accompanied by corresponding changes in precipitation. From a more technical meteorological perspective, it's sometimes defined as a complete replacement of dry, hot continental air by moist, equatorial maritime air up to an altitude of 3 to 5 kilometers over land and water surfaces.
Okay.
But perhaps a more holistic view, like that proposed by climatologist Peter Webster, sees the monsoon not just as an atmospheric phenomenon, but as a fundamental response of the entire coupled land-atmosphere-ocean system to the annual cycle of solar radiation. It involves complex interactions and feedbacks between all these components. Some newer theories even challenge the traditional view that the simple land-sea temperature contrast is the sole driver, suggesting other factors like the elevated heating effect of the Tibetan Plateau are equally, if not more, important.
So it's the whole Earth system working together.
That's the modern perspective, yes. Some common characteristics you see in monsoon systems worldwide include those massive summer rains followed by very dry winters, the distinct seasonal wind turnaround, large transfers of moisture across the equator, and often a strong influence from regional geography, like mountains, which can enhance rainfall dramatically.
And the impacts are huge.
Immense globally. Most agriculture and economies in monsoon regions are intimately tied to these rains. And the internal variability when the monsoon starts, the onset, how strong it is, those active break cycles can be catastrophic if it deviates too far from the norm. It really highlights its profound importance.
Right. You mentioned disturbances like depressions. How do they relate to the active break cycles?
That's another area of active research and debate. Are the active and break phases simply a result of the inherent dynamical uncertainty or chaos in the large-scale monsoon flow? Or are they more directly tied to the life cycle, the formation, propagation, and decay of those monsoon depressions and the north-south shifts of the monsoon trough?
Cause or effect.
Exactly. We know the daily rainfall is fundamentally linked to these synoptic scale disturbances, like lows and depressions, zones where air converges, and the interaction of the monsoon flow with topography. Or ography. The frequency, intensity, track, and lifespan of these disturbances largely dictate the regional distribution and amount of rainfall. During pronounced break periods, there's typically a noticeable lack of new monsoon disturbances forming over the key regions like the Bay of Bengal.
Fewer storms means less rain.
Generally, yes. These disturbances range in intensity from just a weak low-pressure area to a well-defined monsoon depression up to occasionally a tropical cyclone. Interestingly, studies have shown there isn't necessarily a significant difference in the number of strong depressions between strong, wet, and weak, dry monsoon years overall. However, strong monsoon years often seem to feature a higher number of weaker low-pressure systems forming, perhaps indicating a generally greater level of instability within the monsoon trough, which leads to more widespread, if not always extreme, rainfall.
Fascinatingly complex.
It truly is one of the most complex and impactful weather systems on the planet.
It's astounding how these massive, often invisible forces, air masses shifting, monsoons reversing, can have such a profound, invisible impact on entire regions and economies. And all this vast movement in the atmosphere, all this moisture being transported, ultimately gives us one of the most beautiful and vital phenomena we see: clouds. They're definitely not just fluffy decorations in the sky, are they?
No, not at all. Clouds are far more than just visual aesthetics. They are absolutely fundamental to our planet's climate, weather, and especially the water cycle. A cloud is essentially a visible cluster, a suspension of incredibly tiny water droplets or tiny ice crystals, or sometimes a mixture of both floating in the air. Their base is usually above the Earth's surface.
Visible water in the sky.
Exactly. While there are some rare types like not dilucent clouds very high up or occasionally cirrus clouds reaching into the lower stratosphere, most clouds we see are confined to the troposphere, that lowest layer of our atmosphere where all the weather happens.
Right. How do they form up there?
They typically form when air containing invisible water vapor rises, expands, and cools. As the air cools, it reaches a point where it can no longer hold all the water vapor it contains. It becomes saturated. This causes the excess water vapor to condense onto those tiny dust particles we talked about earlier, or other microscopic particles called condensation nuclei, forming visible liquid water droplets, or, if it's cold enough, depositing directly as ice crystals.
So rising, cooling air is key. What makes the air rise?
Several mechanisms. Convection is the big one. That's when the sun heats the ground heats the air just above it, making it warmer and less dense than the surrounding air, so it rises like a hot air balloon. This often forms puffy, cumulus clouds.
Okay, surface heating.
Air can also be forced to rise when it encounters a barrier, like a mountain range. This is called orographic lifting, and it often creates clouds and precipitation on the windward side of mountains.
Pushed up by mountains.
Right. And large-scale atmospheric movements associated with weather systems, like warm air gliding up over colder air along a warm front, or air converging into a low-pressure system and being forced upwards, also lead to widespread cloud formation, often producing extensive layers of stratus or nimbostratus clouds.
So different ways to get the air moving up.
Exactly. Now, to be a bit more precise about what's in a cloud, it's a visible mass of these minute droplets of water or tiny splinters of ice or a mixture hanging freely in the air. These droplets are incredibly tiny, often just 1/100 of a millimeter in diameter. You could fit millions of them in a cubic meter of air.
Millions.
Yes. And what's really fascinating is that these microscopic liquid droplets can remain liquid even at temperatures well below freezing, down to as low as -30, even -40 degrees Celsius in some cases. We call these supercooled droplets.
Liquid water below freezing, yeah.
It's because freezing requires not just cold temperatures, but also suitable ice nuclei, tiny particles with a crystal structure similar to ice for ice crystals to start forming around. In very clean air, or for very tiny droplets, these nuclei might be scarce, allowing the water to stay liquid far below its normal freezing point. Eventually, though, they will freeze or evaporate.
Okay, that's wild. How do we classify all the different clouds we see? They look so varied.
They are incredibly varied. Their systematic classification actually dates back over 2 centuries. A Frenchman named Lamarck proposed a classification in 1802, but it was an English amateur meteorologist, Luke Howard, who in 1803 published a classification strategy based on Latin names for basic shapes that became the foundation for the modern system we still use today.
Based on shapes.
Yes, he identified 3 fundamental forms. Cirrus, from Latin for curl or hair, describing thin wispy clouds. Stratus, from Latin for layer or sheet, describing flat, featureless clouds, and cumulus, from Latin for heap or pile, describing puffy, lumpy clouds. He also added nimbus, from Latin for rain cloud, to denote clouds that were actively producing precipitation.
Cirrus, stratus, cumulus, nimbus. The basics.
Those are the building blocks. Today's classification, used by meteorological organizations like the UK Met Office and others worldwide, builds on Howard's system. It primarily classifies clouds based on the altitude of the cloud base, dividing them into 3 main levels: high-level, mid-level, and low-level clouds. Within each altitude category, specific cloud types are named using combinations and variations of those 4 basic Latin terms to describe their appearance and sometimes their structure or precipitation characteristics.
Altitude plus shape. Okay, let's break that down. Low-level clouds first.
Okay, low-level clouds. Their bases are generally found below about 6,500 feet or 2,000 meters. The most common types here are cumulus clouds. These are those classic detached, puffy, cotton-like clouds with flat bases and bulging upper parts, often seen on sunny days. They usually form between 1,000 and 5,000 feet, initiated by surface heating, convection. They generally indicate fair weather, though larger ones, cumulus congestus, can grow vertically and produce showers. Stratus clouds. These form as grayish, featureless, uniform sheets or layers, often covering the entire sky like fog that doesn't reach the ground. They typically form very low, from the ground up to about 2,000 feet. Thick stratus can produce light drizzle or snow grains, especially in hilly or coastal areas, and they often obscure the sun or moon completely. Stratocumulus clouds. These appear as low, lumpy, grayish or whitish layers or patches, often with dark undersides. They look like rounded masses or rolls, sometimes arranged in waves. They form at similar altitudes to stratus and cumulus, usually between 1,000 and maybe 7,000 feet. They rarely produce significant precipitation, maybe just light drizzle, but can be thick enough to obscure the sun or moon. They often form when stratus layers break up, where cumulus clouds spread out horizontally.
Okay, cumulus, stratus, stratocumulus down low. What about mid-level?
Mid-level clouds. Their bases are usually found between 6,500 feet, 2,000 meters, and about 20,000 feet, 6,000 meters. Because they form at altitudes where temperatures are often between 0 degrees C and -40 degrees C, they're typically composed of a mixture of supercooled water droplets and ice crystals. The prefix alto is often used for mid-level clouds.
Alto means middle.
Essentially, yes. The main types are altostratus clouds. These are grayish or bluish sheets or layers of fibrous or uniform appearance, often covering the entire sky. They are denser than high-level cirrostratus. They often precede storms with continuous rain or snow. While they usually hide the sun or moon, sometimes the sun-moon might be visible through thinner patches as if viewed through ground glass. They typically form between 10,000 and 20,000 feet and can produce light, continuous precipitation. Altocumulus clouds. These appear as white or gray patches, sheets, or layers, generally with a waved or rounded appearance, like sheep clouds or a mackerel sky. They form between 6,500 and 20,000 feet. They are usually composed mostly of water droplets, but can contain ice crystals. They don't usually produce much precipitation, but their presence can indicate changing weather. Sometimes they can be thick enough to hide the sun or moon. Nimbostratus clouds. Now, these are the main precipitation producers among the layered clouds. They are dark gray, often menacing, thick, amorphous rain clouds. Their bases are typically in the low to mid levels, anywhere from near the surface up to 10,000 feet, but they are thick enough to blot out the sun completely. They are associated with continuous, usually light to moderate, rain or snow falling over a wide area, often ahead of a warm front. The nimbo part signifies rain producing.
Nimbostratus, rainy layers.
Yeah.
And high up.
High-level clouds. Their bases are generally found above 20,000 feet, 6,000 meters, where temperatures are typically below -40 degrees C. Because it's so cold, they are composed almost entirely of tiny ice crystals. The prefix cirro, or the word cirrus itself, denotes high-level clouds.
Cirro means high and icy.
Exactly. The main types are cirrus clouds. These are the thin, wispy, feathery clouds made of ice crystals, often looking like delicate white filaments, patches, or narrow bands. Maris tails. They form very high, typically between 20,000 and 40,000 feet. They don't produce precipitation that reaches the ground, although you might sometimes see faint streaks of falling ice crystals, called fall streaks or virga, below them. They are famous for creating beautiful optical effects like halos around the sun or moon, caused by the refraction of light through the ice crystals. Cirrostratus clouds. These are thin, sheet-like, high-level clouds, also composed of ice crystals. They often cover the entire sky, giving it a milky appearance. They're usually so thin that the sun or moon can be clearly seen through them, and they are well known for producing prominent halos. Their appearance often indicates that moist air is rising at high levels and can be the first visible sign of an approaching warm front and deteriorating weather. Cirrocumulus clouds. These appear as thin, white patches, sheets, or layers composed of very small ripples or grains, often arranged in a pattern, like tiny ripples on sand. They are less common than the other cirrus types and also indicate high-level moisture and instability.
Wispy cirrus, sheet-like cirrostratus, rippled cirrocumulus. All high and icy.
That's the idea. So you have this whole classification system based on altitude and appearance, helping us understand the processes happening in the atmosphere.
It's amazing how much information is packed into just looking at the clouds.
It really is. They tell a story about the air's movement, its moisture content, its temperature profile.
This raises an important question, though, connecting back to our earlier discussion. How do these dynamic atmospheric systems, the air masses moving, the monsoons pulsing, the clouds forming and raining, how do they directly influence the powerful forces we talked about deeper down, like the Earth's crust and its molten core? And maybe vice versa. How does activity deep within the Earth influence the atmosphere above?
That's a fantastic question, highlighting the profound, intricate connections across all of Earth's systems. They aren't isolated compartments.
Right. It feels like we should connect the atmosphere back to the Earth's inner workings, maybe through something really dramatic.
Well, perhaps the most dramatic visual link between the Earth's molten interior and the surface environment, including the atmosphere, is a volcano.
Perfect. That brings us full circle, doesn't it? From the slow, creeping dance of tectonic plates, the sudden, violent shudder of an earthquake. Our planet definitely has many ways of showing its power. But yet, perhaps none is as visually dramatic as primal as a volcano erupting.
It's certainly captivating and often terrifying.
When most people imagine a volcano, they probably picture that classic, steep, cone-shaped mountain
Yeah.
spewing fiery lava, right? Like Mount Fuji or Mount St. Helens.
That's the iconic image, the stratovolcano.
Right, but you're saying, like with clouds, there's more variety. That classic cone is just one vintage in a whole diverse collection of volcano shapes and sizes.
Exactly. The source material nicely calls it a zoo of volcano shapes and sizes, and that's pretty accurate. The form a volcano takes depends heavily on the type of magma erupted, the style of eruption, and the geological setting.
Okay, so fundamentally, what is a volcano?
Simply put, a volcano is basically a vent, an opening in the Earth's crust through which molten rock, magma, gases, and ash escape from the Earth's mantle or crust onto the surface. As this material accumulates around the vent, it often builds up a mountain or hill, which we also call a volcano.
So it's the vent and the structure built around it.
Correct. They often take on that familiar cone shape, but as we'll see, they can vary quite a bit. They form when this molten, often sticky rock, magma, forces its way up through cracks or weaknesses in the Earth's surface. Once that melted rock erupts and flows out onto the surface, we call it lava. And lava is incredibly hot, obviously, destroying pretty much everything in its path.
Where do they form? Mostly on land.
Most of the volcanoes we see are on land, often concentrated along those plate boundaries we discussed, especially convergent subduction zones and divergent rift zones boundaries. Think of the Ring of Fire around the Pacific Ocean. However, many, many more volcanoes are actually on the ocean floor, particularly along the mid-ocean ridges. We just don't see most of them. Some submarine volcanoes grow tall enough to eventually rise above the water surface and form volcanic islands like Hawaii or Iceland.
Hawaii is volcanic islands.
Entirely. Formed over a hot spot deep in the mantle, not directly at a plate boundary. That's another way volcanoes can form.
Okay, and what triggers an eruption? Why does it suddenly blow?
An eruption happens when the magma accumulating beneath the surface, along with trapped gases like water vapor and carbon dioxide, finds a pathway, a vent, to escape the intense pressure underground. As magma rises toward the surface, the pressure decreases, allowing those dissolved gases to expand rapidly, like opening a shaken soda bottle. This expansion can drive explosive eruptions, or if the gas escapes more easily, the magma might just flow out more gently as lava. Eruptions, therefore, vary hugely in style, from relatively gentle lava flows to incredibly violent explosions that can blast ash and rock tens of kilometers into the atmosphere.
Okay, gas pressure is key. Let's get into that zoo then. What are the different types of volcanoes?
All right, let's explore some of the main varieties, highlighting their unique characteristics. First, shield volcanoes. These are typically very large, broad volcanoes with gentle, rounded slopes resembling a warrior's shield laid flat on the ground. Think of the Hawaiian volcanoes like Mauna Loa and Mauna Kea. They're the classic examples.
Gentle slopes, not steep cones.
Exactly. They can grow to be truly enormous. Mauna Loa, measured from its base on the deep ocean floor, is one of the most voluminous mountains on Earth, rising over 30,000 feet and stretching maybe 100 miles across at its base. They are built up almost entirely by countless eruptions of very fluid, low-viscosity basaltic lava flows that travel great distances from a central summit vent or flank vents before solidifying.
Fluid lava spreads out far.
Right. Because the lava is so fluid and gas escapes relatively easily, shield volcano eruptions are typically effusive, meaning characterized by lava flows rather than explosive. They don't usually produce much pyroclastic material, ash and fragments. This generally makes them less hazardous to be near during an eruption compared to explosive volcanoes, though the lava flows themselves can obviously destroy property.
Okay, big, broad, flowing lava. What's next?
Then there are flood basalts, or large igneous provinces, LIPs. These represent Earth's largest known type of volcanic event in terms of sheer volume of magma erupted. These aren't single volcanoes, but vast outpourings of extremely fluid basaltic lava from long fissures or multiple vents, covering huge areas of land or ocean floor with thick stacks of lava flows.
Covering huge areas.
Huge areas. Think hundreds of thousands, even millions of square kilometers. Examples include the Deccan Traps in India or the Columbia River basalts in the U.S. Pacific Northwest. These eruptions happen over relatively short geological periods, maybe a million years or so, but the eruption rates can be immense. Thankfully, none have occurred in human history, though they have happened periodically throughout Earth's past.
Good thing. What are the hazards?
Well, the main immediate hazard would be the sheer scale of the lava flows burying vast landscapes. But perhaps more significantly, the colossal amounts of volcanic gases, particularly carbon dioxide and sulfur dioxide, released during these events are thought to have potentially caused major global climate change and even mass extinctions in Earth's history.
Wow, climate-changing eruptions. Okay, something smaller maybe.
Okay, back down in scale, we have scoria cones, which are often also called cinder cones. These are typically the simplest and most common type of volcano. They are relatively small, conical hills, usually only a few hundred feet to maybe 1,000 feet high, with steep sides and often a bowl-shaped crater at the summit.
Small and steep. How do they form?
They are typically formed by mildly explosive eruptions, often called strombolian eruptions, characterized by fountains of lava fragments being ejected from a single central vent. These fragments, called cinders, or scoria, which is why they have two names, are blobs of gas-rich basaltic or andesitic lava that cool and solidify quickly as they fly through the air. They fall back to the ground around the vent, accumulating to form the cone shape.
Built from ejected bits.
Exactly. They are often formed during a single eruptive episode that might last from a few weeks to a few years. Once the eruption stops, that particular cone usually doesn't erupt again, although new cones might form nearby later. They often occur as parasitic cones on the flanks of larger volcanoes like shield volcanoes or stratovolcanoes.
Okay, simple cones. What about the classic ones?
Right, the ones most people picture, stratovolcanoes, which are also very commonly known as composite volcanoes. These are the majestic, tall, steep-sided, often symmetrical cones like Mount Fuji, Mount Rainier, or Mount Vesuvius. They can reach impressive heights, sometimes over 10,000 feet.
The picture-perfect volcano.
Often, yes. They are called composite because they are built up from alternating layer strata of different volcanic materials. Hardened, viscous lava flows, typically andesite, dacite, or rhyolite, mixed with layers of pyroclastic deposits like volcanic ash, cinders, and bombs ejected during more explosive phases.
Layers of lava and ash.
Exactly. Because they often erupt more viscous, stickier lavas compared to shield volcanoes, gases can get trapped more easily, leading to a buildup of pressure and often resulting in highly explosive eruptions. Their eruption styles can vary widely, from relatively mild volcanic eruptions to catastrophic Plinian eruptions that send huge ash columns high into the stratosphere.
More dangerous then?
Generally, yes. Stratovolcanoes account for about 60% of the Earth's active land volcanoes and are responsible for some of the most destructive volcanic hazards, including devastating pyroclastic flows, those fast-moving avalanches of hot gas and volcanic debris, dangerous lahars, volcanic mud flows, widespread ashfall, and sometimes lava flows. They are common along subduction zones, forming those volcanic arcs we talked about.
Okay, the big explosive cones. Any other main types?
A few more worth mentioning. Feeder volcanoes, we touched on with flood basalts, but on a smaller scale too. These lack a central crater. Instead, eruptions occur along long linear cracks or fissures in the ground. Lava, often very fluid basalt, erupts along the length of the fissure, sometimes creating spectacular curtains of fire. The lava spreads out widely, often forming flat plains or plateaus rather than distinct cones. The source rifts usually get buried by the lava, so afterwards there might not be an obvious volcano-like structure left behind. The 1783 Lakoe eruption in Iceland was a major fissure eruption.
Erupting from a crack, not a point.
Exactly. And then there are lava domes, also called volcanic domes. These are often formed after a major explosive eruption from a stratovolcano has cleared the main vent. The remaining magma is often thick, viscous, and degassed low colloids. This sticky magma oozes out slowly, piling up around the vent to form a steep-sided rounded mound or plug the lava dome.
Like a cap on the volcano.
Sort of, yeah, filling the crater or building up on the flank. They can form relatively quickly, sometimes in just hours or days, or they can grow slowly over months or even decades. Lava domes themselves can be quite hazardous because they are inherently unstable. They can collapse suddenly, generating dangerous pyroclastic flows, or they might extrude short, thick lava flows, or be associated with explosive activity if pressure builds up beneath them. Mount St. Helens famously grew a lava dome inside its crater after its 1980 eruption.
So even the leftovers can be dangerous.
Absolutely. So you see, from the vast shields to the tiny cinder cones, the layered stratovolcanoes to the oozing domes and cracking fissures, there's a remarkable diversity in how Earth's internal heat manifests itself at the surface.
It really is a whole zoo. What's truly fascinating here is that sheer diversity, each feature a unique expression of the Earth's internal heat and pressure, constantly reshaping our world in these dramatic and often powerful ways.
Couldn't agree more. Each type tells a different story about the magma beneath and the tectonic setting.
So let's try and pull this all together. From the pervasive presence of geography in our daily lives, through the protective embrace of our atmosphere with its layers and movements, the deep rumblings and slow crawl of tectonic plates causing earthquakes, the intricate dance of air masses and monsoons driving our weather, to the very rocks that form our crust and undergo that endless cycle, and finally, the dramatic release of internal heat through volcanoes. Wow, we've covered a remarkable amount of ground today.
We certainly have. It's a whirlwind tour of Earth's dynamic systems.
And we really hope this deep dive has given you, our listener, that shortcut to being truly well-informed about the dynamic planet we call home. Hopefully providing some of those aha moments, maybe some memorable details you were looking for.
And if we connect this all back to that bigger picture, what becomes really evident, I think, is that the Earth's systems, its atmosphere, its deep interior, its moving plates, its winds and waters, its rocks, they are not isolated phenomena operating independently.
Right, they all interact.
Exactly. They are parts of an incredibly intricate, self-regulating, continuously interacting network. Everything influences everything else, often through complex feedback loops operating over vastly different timescales. And thinking about this interconnectedness, this constant change, raises an important, perhaps slightly unsettling question. Given these constant fundamental forces at play, the heat flow from the core, the slow grind of tectonic plates, the circulation of the atmosphere and oceans, the relentless cycle of rock transformation, how much of what we perceive as stable or permanent on our planet's surface is merely a momentary equilibrium? Just a snapshot in an ever-changing, ongoing geological and atmospheric dance that has been playing out for billions of years and will continue long after us.
Wow. Is stability just an illusion in the long run? This is some profound to mull over, for sure. Thank you for joining us in this deep dive with Knowledge Flow.
Thank you.
Until next time, keep exploring.